And we will directly continue with the next part that is concerned with the MCE, which stands for Memory Cipher Engine. The focus will be put on how to make sure the code and data in the external memory is encrypted and thus protected. So in a situation where security is not a concern, we have a code and data in the external memory, and the MCU is interfacing the external memory over the XSPI interface. Without protection, the external memory content is fully accessible to anyone who can connect on the XSPI bus or read the external memory. This makes it possible for an attacker to basically dump our application firmware. To avoid this, we can use the Memory Cipher Engine that is able to perform hardware on-the-fly encryption and decryption of the code and data, provided that the interface is configured in the memory mapped mode. So then the core and internal peripherals will see only decrypted data, so no issue there, and only decrypted data, yeah, and only encrypted data will be stored in the external memory. The question is how to put the encrypted image with code and data to the external memory, and for that we will use the external memory loader, but we will have to do some modifications to make sure that it's encrypting the firmware and the data transferred to the external memory. So let's get some overview of the Memory Cipher Engine. There are 3 different modules. Each module is covering one peripheral. So we have MCE1 for the XSPI1, MCE2 for XSPI2, and MCE3 for FMC, which is the parallel interface to connect parallel memories. So the aim is to protect the external memory, like a NOR or a NOR flash or SRAM. We can have up to 4 encrypted regions for each Memory Cipher Engine. We have some flexibility in the cipher configuration, so from 0 latency stream cipher to side channel protected block cipher. And it can act also as an embedded firmware. So for example, we can have a read-only access. So the encryption works in this direction, okay? And the decryption, of course, in the opposite, and then the core and the peripherals, they will see only the decrypted data. So the MCE1 is using the AES, and the remaining 2 MCE modules are using Nakion. There are some pros and cons of each of these symmetric key block ciphers. So for example, AES is known for its high security and standardized, and it's widely adopted, while Nakion is, let's say, very efficient, simple, and as fast in hardware. It is a bit faster than AES, and it provides some side channel attack resistance. AES, and this is very important, it supports the stream mode, mainly used for flash memories, which can heavily increase the performance of the decryption. So let's say it is advisable to connect your external flash memory if you use the execute in place and you want to have an encrypted code and data in the external memory, to connect it to XSPI1 for the maximum performance, because this one can support the stream mode for the decryption. Okay, each Memory Cipher Engine can define up to 4 regions with certain granularity, and each of these regions is defined by its address range and the crypto configuration. And as a result, we can have only a part of the external memory encrypted, or selected parts of the external memory. MCE encrypts the external memory in memory mapped mode. And to write to an external NOR flash, a specific code sequence is required, and it must be ensured that the process is not interrupted. And for that reason, we will use the DMA, because with the core to write, so this will be used by the external memory loader to program our application firmware encrypted to the external memory. So to write, we need to make sure that this process is uninterrupted, and this we cannot guarantee with the core, because we can get some interrupt and so on. So we will use the DMA. So external memory loader and the MCE. So by default, without encryption, the external memory loader programs the external flash memory using the XSPI interface in command mode. So it's not memory mapped. But in order to use the encryption, we need to use the memory mapped mode, which means that we will have to override the memory write function to use a memory mapped mode for memory programming. And for the rest, it will use the indirect or command mode for actions like unlock or erase. And we also will have to override the memory copy function to use DMA and to ensure that the constant 16-bit write is done for the MCE. So it writes in blocks and it encrypts these 16-byte blocks and 256 bytes for the memory. So this is required by the memory to write in these blocks. And we will, of course, have a memory protection unit configured to avoid access to an unmapped region. So that's all for the theory. Let's begin the practical part. So I am here in the GitHub page. I go to memory Cipher Engine part. Introduction. This is again mainly the theory that has just been presented to you. But what is important here is that in this part we have two different kinds of projects. So here in this hands-on, I will start from the previous project and add the MCE on top of the already completed project from the first part. But in case you did not succeed or you don't have this project available, you have the complete project here, and the actions necessary are just to uncomment different parts according to the step-by-step guide to make it working. So this is the easiest part, how to get it working on your end. So let's go to the CubeMX part. So I open the CubeMX project, and we will enable the memory Cipher Engine 1 for the bootloader and external memory loader. So I switched here to the alphabetical order so that it's easier for me to find this peripheral. I will enable it for the bootloader and for the external memory loader. Okay. I will check activate it. And that's all for the MCE. And then the DMA. So I go to HP DMA1. And here I select the channel 15 in standard request mode. You could use any channel, but our code is prepared to use the channel 15. So this is just to, let's say, make sure that the library, the driver for the DMA will be included in the project. The rest will be done by the code. And the standard request mode, this is basically a legacy mode that simple DMA transfers. The DMA also supports so-called linked list mode, where we can configure, let's say, more complex scenarios with different DMA transfers chained thanks to the linked list. So to have quite an autonomous operation of the DMA. Okay, so the standard request mode. And that's all for the CubeMX part. So I will regenerate the code. So regenerate our previous project. Okay, and it's finished, finally. So I open the project. And I have it here. Now, I will go to the bootloader main.c file. So bootloader main.c. And I will add the key, the simple key there. Then I will add the MCE configuration. Here to the part where we initialize all the peripherals. And in this part for the bootloader, it's configured as a read-only. So it's AES. We are using the MCE1. We are using the key that we defined above. This can be even stored somewhere in the OTP in the real application, but here for simplicity is done like this. It's over the entire external memory. So you may remember the boundary address for this NOR SPI flash. And it's read-only because the bootloader will configure the MCE, and then when it will hand over the execution to the application, we will only read from the memory. We will execute the code from there. Okay, then cache invalidation is already there from the previous part. Then we will go to the external memory loader, to this file external memory loader init. So external memory loader or init. It's opening. And again, I will add the key there. The same key. Then the MCE configuration. Here the only difference is that it will be both read and write is possible, because the external memory loader, this is the one who needs to transfer the encrypted firmware to the external memory. So I go to the user code section 2. Here. I copy this part of the code. And then we need to redefine the memory write function. So the default implementation is weak, which means that we can use our own definition. And here, in case that the size is larger than the max page write, so which means that we are, let's say, transferring the complete firmware to the external memory, we will use the memory mapped mode. In other cases, it will use the indirect mode, or command mode. So I'll put it here. So this is the memory write, and then we also have to redefine the memory copy function. Again, the default, I can show you the you can see that the default implementation is weak, so we can replace it. I can go back to this file, and we will use the DMA here. So the DMA to write to the external memory, because we need to ensure that there is this defined sequence, and then that it is not interrupted. And this memory write, it decides whether to use the memory mapped mode or indirect mode. And then later on, in case of the memory mapped mode, it calls this external memory memcopy function. So this function is used in the memory mapped mode. And we will make sure that we use the DMA to write to the external memory. Okay, then we will add some buffer just to make sure that the DMA reads are properly aligned. So it's probably not necessary, but it's to make sure. So I'm adding it here with the key. Then we will include the, here, the memory wrapper to be able to overwrite those memory write and external memory copy functions. And then we will use the MPU to disable the write access to the external memory by the core. So we will use the DMA to write there, and let's say to make sure that it's not interrupted by the core trying to access the external memory. We will use the MPU and make sure that the core doesn't have a write access to the external memory for this part. So this is to be put to the user code section 1. at the beginning. And then here we can disable the instruction and data cache. This is done because the external memory loader, it's running from the SRAM. So while it's being used, it's loaded in the SRAM, into the SRAM of the microcontroller, which is fast enough, and there is no real reason to use this cache by the external memory loader. And we will also comment out this HAL MPU disable because we want to this MPU configuration to be taken into account. And that's all. So now I can build all the projects. And then we can test if it's still working. So meanwhile I connect with the Cube programmer just to check my option bytes configuration. Yeah, it's fine. Yeah, there will be some warnings, so we definitely have to work on that to improve this this code example. But it should build all the projects without errors. Okay, now I can start debugging. And I need to use a new external memory loader. So the one that we have just generated. So I'm in the folder with my project. I go to external memory loader, debug, and you can see that this one is the old loader from this morning. So I will take this L file that we have just generated. I will rename it to the required format, to here. I can show you that I have to close my camera. That right now the board is not doing. It is, sorry. I have to. I will erase the code. Yeah, you can see here that there is still the application from this morning. So I will do the mass erase. Now it's achieved. Now you can see that the flash is empty. So if I switch back, you can see that the LED is not toggling. I go back to the IDE. Here I need to select the right loader, so the new one. And in the startup, this is already configured. So I click on apply and debug, and we will start the debug session. Okay, it seems I have some problem here. Just try to reconnect the board quickly. Yeah, I forgot to disconnect with the Cube programmer. Now it's fine. And as you can see, we have a breakpoint at the beginning of the boot. I can show you that we are inside the internal flash. Hopefully you can see it. I can go to the application, the same as before, and put a breakpoint there. So I go there and you can see that now we are in the external memory. If I click on run, then you will see that the LED is toggling. And if I open the memory window, I put the address. I have to. So you can see that inside the external memory, the first value, this is the initialization for the stack pointer, and then we have some addresses of the interrupt vectors and so on. So it's not encrypted because we are using the memory Cipher Engine to decrypt on the fly. So the core and internal peripherals, they see only the decrypted data. So I will now go to the MCE1, and I need to find the right bit to disable the encryption. I think it's this one. And if I do a step now, you can see the encrypted data because I switched off the memory Cipher Engine. And now when I try to access this external memory, I see the encrypted data. So I will terminate the debugging. I will also connect using the QProgrammer. Here on the bottom left, we have external loaders, so I can find the one for this board. Yeah, it's this one. It's already selected. So I go back here, and I can try to read from this. From this address, and you can see the encrypted data inside. Inside the external memory. I can go back and select this select, okay. Okay. If I select the one that I generated yesterday and I moved it to the QProgrammer folder, I go back and read the data. You can see that I read the decrypted data because the default loader here, the default one here below, this one, it's not using the memory Cipher Engine. It's not using on-the-fly encryption and decryption. But the one that I generated yesterday, which is the same one which we generated today, it's using the MCE, so I can read the decrypted data. Okay. And I can show you that the application is running like before when we used no encryption. So I will now stop. So that's all for this part. So in this part, we learned how to use the new peripheral memory Cipher Engine that now can work on both directions and can encrypt and decrypt the data in the external memory on the fly, the data and the code as well. We learned how to modify the bootloader to use the MCE to encrypt the data and how to modify the external memory loader to use the DMA to write to the external memory and to use the MCE to encrypt the data. So thanks a lot for your attention, and we will now move on to the last practical session, which deals with the debug authentication, so another security feature.